Hi everyone, welcome back. Let's continue on sessions 8.1. Let's look at this example. Similarity graphs. Grouping like objects into classes based on properties of the objects. So suppose a particular algorithm is implemented in C++ by a number of persons, and we aim to group like programs into classes based on three rules. First, the number of the lines of code. Second, the numbers of return statements, and the number of functions called. So based on the data, we can get a table. So this is the table. We have 5 programs that we want to compare. Okay? And we collect the data about the lines of codes and the number of return statements and the number of function calls. Okay, we want to measure how similar they are. Okay, so now each program can have an order triple, okay, to describe it. We can denote by the vertex v1 equals, so the order triple, so p1, p2, p3. Okay, so this is p1, this is p2, this is p3. So where pj is the value of the property j. Okay, for each pair of the vertex, let's say v is p1, p2, p3, and w, the vertex w has the property q1, q2, q3, then we can define a similarity function. Okay, S of VW is the difference between all the properties. Okay, so the absolute value of P1 minus Q1 plus absolute value of P2 minus Q2 plus absolute value of P3 minus Q3. Okay, so after we define these similarity function, we can find those values. Okay, so here, how many possible ways we can have? Well, we want to pick 2 vertices to compare, and we have 5 vertices, so 5 vertices we pick 2. So what is that? 5 choose 2, that is 5. We count down 4 divided by 2, so 10 different pairs. Right, everybody? So here are the 10 different pairs. I already put it down. So let's calculate. V1 and V2. So V1 and V2, okay, we have the difference between 66 and 41. So 66 minus 41 is 25. Okay? And then next, 20 and 10, the difference is 10. And then we have 1 and 2, the difference is 1. So because it's absolute value, so absolute value of 1 minus 2, absolute value of negative 1 is 1. So when you find the difference, you just find the bigger number, subtract the smaller number, then we can get the positive difference between them. Okay, so 25 plus 10 plus 1, that gives us 36. Okay, so the similarity between them is 36. Okay, next, V1 and V3. V1 and V3. So we have 66 and 68, right? 66, 68, difference is 2. And 20 and 5, the difference is 15. Okay. And then we have 8 and 1, the difference is 7. So what is our answer? 17 plus 7, that is 24. So you can see that this similarity is 24, which is less than the 36 we calculate between V1 and V2. Alright, let's continue. V1 and V4. So V4 is right here. 66 and 90, the difference is 90 minus 66, 24. And then 34 and 20, the difference is 14. 5 and 1, difference is 4. So add those numbers up, we get 34 plus 4, 42. Right, 38 plus 4, 42. Okay, let's continue. V1 and V5. So 75 minus 66 is 9. 12 and 20, so 8. And then 13, right? So 9 plus 8 is 17, plus 13, 30. Okay, and then next we have V2 and V3. 41, 68, that is 27. Okay, so you can pause the video and try to calculate your answer, and then you can continue to play the video and check our work together, right? So that's 11, so 38. Next, V2 and V4. So that gives us 49, and 34 minus 5 is 29. 5 plus 8, 13. Wow, this is a big number. Okay, I'm gonna borrow 1 from 13. I get 50. Borrow 1 from 13, we get 30. So that's 80 plus 11, 91. Let me see. Oh, I see I make a mistake. This is 4, actually. Sorry. So this will give us 73 plus 13 is okay. Where do I? Oh, and this, I must look at the wrong line. Okay, this is only 3. So 73 plus 3 is 76. Okay, 2 and 5. So sometimes when we work with a lot of numbers, it's good to check our work. Okay, go back and check our work, because when we make mistakes, we check our work, we find our mistakes, then we can learn from it. 75 minus 41 is 34. 12 minus 10 is 2. And then 14 minus 2, 12. So 36 plus 12, 48. So far, so good. Okay, next we have vertex 3 and vertex 4. Okay, 90 minus 68, that is 22. 34 minus 5, 29. 8 minus 5, 3. 25 plus 29 is 54. So far, so good, everybody. Okay, continue. Vertex 3 and 5. 75 minus 68 is 7. 12 minus 5 is 7. 14 minus 8, 6. So, the answer is 20. This is the smallest number we get so far. Okay, finally, vertex 4 and vertex 5. 90 minus 75, 15. 34 minus 12, that's 22. And then 14 minus 5, 9. This is 37. So 46. Okay, so we have found all the dissimilarities between different vertices. And we have 10 pair of vertices. So this function helps us to measure how dissimilar the two programs are. We could say 2 points V and W are as being connected, or the dissimilarity less than S for where S is some value. Okay, being connected. Okay, so let's see. I think I have typo here. Okay, so we can define the 2 points are connected if the similarity is less than some value. Okay, and then they are in the same class if v equals w or there is a path from v to w. Okay, so show the path with s equals 25. So here we have 5 programs, right? So we have 5 vertices. So let's say V1, V2, V3, V4, V5 here. Okay, so if the dissimilarity between the 2 vertices is less than 25, then we build an edge between them. So V1 and V2, the similarity is 36, so no edge between them. And then V1, V3, the similarity 24, so there is an edge between V1 and V3. Okay, and then next one, V1, V4, 42 is so big. V1, V5, 30 is so big. V2, V3, 38 is so big. V2, V4, 76 is big. And then 48 is big, 54 is big, 20 is small. So V3 and V5, there is edge connecting them. And then 46 is big. Okay, so for when the dissimilarity is less than 25, we build a edge between those 2 vertices. Okay, so this is the graph we get. And here you can see there are 3 classes. Okay, and there are also 3 components. Okay, so this guy is connected, it's one component. This guy is one component. This guy is another component. So, and these 2 are the isolated vertices. Okay, so we have 3 classes. They are vertex 1, vertex 2, vertex 1, vertex 3, and vertex 5. Okay, and then the vertex 2 is by itself, vertex 4 is by itself. So we have 3 classes. Okay, so far so good, everybody. And I also want to put a remark here. So you notice that V1 and V5, so they are not adjacent. Okay, even though V1 and V5, where's V1 and V5? Here, the similarity is 30, but even though they're not adjacent, but there is a path connecting them. Okay, so but there is a path connecting them. So they're in the same classes or components. Okay, so they're still in the same class. So far so good, everybody. Okay, you might want to ask, why do I leave so much space here? Because I want to draw some picture to show you what happened if we pick another number as the dissimilarity. Let me use green. Okay, so let me use the green here. If s is 40, so instead of 25, if we pick s to be 40, how would our picture change? Okay, so we have V1, V2, V2 is here, V3, V4, and V5. Okay, so V1, V2, 36 less than 40, so we have an edge connecting V1 and V2. And then 24 is small, so V1, V3. V1, V4 is 42 greater than 40, so we don't have an edge. V1, V5, 30, so there's an edge between them. V2, V3, there's an edge between them. Oh, okay. And V2, V4, there is an edge there's no edge between them. 76 is a lot. V2, V5, 48 is a lot. 54 is a lot. V3, V5. V3, V5 is here. Okay, and V4, V5, 46 is big. Okay, so now you can see this is our new picture. And you can see we have two classes in this case. Okay, the first class is V4 by itself, and then we have V1, V2, V3, V5. Okay, so you can see the value of this similarity we pick, then the graph could be different. Okay, so this is this similarity graphs. When we want to compare like different like programs or stuff. Okay, let's continue. The complete graph on n vertices denotes Kn is the simple graph with n vertices in which there is an edge between every pair of distinct vertices. Yeah, we talked about that in our first video, right? So in a regular graph, every vertex has the same degree. So we can speak of the degree of the graph. And the complete graph is a special kind of the regular graph because in a complete graph, like every vertex is connected to all the other vertices. And there are n vertices total. So that's why each vertex, how many vertices that you're connecting it? N minus 1 vertices. So n minus 1 the other vertices. That's why each vertex, they have the degree is n minus 1. So far, so good, everybody. Next, the graph G equals VE is biparty. If there exists subsets x1 and x2 of V such that x1 and x2 are distinct and their union is V and each edge in E is incident to one vertex in x1 and one vertex in x2. Okay, so the biparty is like we have two sets, x1 and x2, and then we have some vertex in there, and then each vertex in x1 is connecting to a vertex in x2 by an edge. Okay, and here we connect by edge. Something like this. Okay, this is biparty. A complete biparty graph on M and M vertex denoted by K sub M comma N is the simple graph whose vertex set is partitioned into set V1 with M vertices and oops, there's one more word. Okay, and V2 with M vertices in which the edge set consisting of all the edges of the form V1, V2 with V1 being an element of V2 and V2 being elements of the set V2. Okay. So let me draw some example here so you can see the difference between biparty and complete biparty. So okay. Okay, so this is biparty. Okay, but it's not complete biparty. Okay, so you can see each vertex in x1 there is a vertex in in x2 such that they're connected by an edge. Okay, so it's biparty, but it's not complete. In order to form a complete biparty, you're gonna have each vertex in x1 is there for all the vertex in x2 there are edges connecting them. Okay, so this guy there's edge connecting both of them. And this edge, there's for that vertex, there's edge connecting both of them. Okay, and you can see what is the number of edges total. Okay, so the number of edges, you can see for for this guy, for each vertex, there are, let's say, if here we have m vertices, here we have n vertices. Okay, then the number of edges is gonna, for each vertex in the set x1, there are n edges connecting it. Okay, so that's why, and we have m vertices in x1. Okay, so each vertex in x1 is connecting to all n vertices in x2. So therefore, we have that vertex is incident to n edges. Okay, and because we have m vertices in x1, so that's why we have n times m. That's the number of edges. So far, so good, everybody. All right, and then let's look at some example. Okay, so I already showed you the picture of biparty and complete biparty. So this guy is complete biparty. Okay, let me show you a picture of a complete graph as well. So let me get back to my orange color. Okay, so I show you before K3, if we have 3 vertex, then we have all the edges connecting them. So this is like a triangle. But how about K4? K4, we have 4 vertices. So each vertex is connecting to all of the other vertices. Okay, so this guy is connecting to this guy, and it's also connecting to that guy. But if you draw it like this, it looks like there is a vertex in the middle. So we can draw it like this. In this case, we can avoid the case that they meet in the middle. Okay, my line looks curvy. Let me make it look better. Okay, so this is a graph of K4, and let me just write down here. So if there is a way that you can try to avoid crossing, then please avoid crossing, because otherwise it looks like there is a vertex there, right? So try to avoid crossing. Okay, otherwise it looks like there is a vertex in the middle. So far, so good, everybody? Okay, and so this is the complete graph. Okay, let's continue. By the way, I'm not saying that we cannot cross the edges. We can cross the edges, but if there is a way we can avoid crossing, try to avoid it. Okay. Next, show the following graph is not biparty. Okay. So we want to show the graph is not biparty. Let's look at the shape here. Do you see there are some shape of rectangle and there are some shape of triangle? Okay, so let's look at this two shape. So look at this two shape. When we have a square, rectangle. Let's say this is V1, V2, V3, V4 in general. Well, can this be a biparty graph? We can have like V1 in the set x, so we have x1 and x2, right? We can have v1 in x1, then whatever is connecting to v1, it should be in x2, okay? So v2 is in x2, v4 is in x2, and then whatever connecting to v2 and v4 must be in x1, so v3 is in x1. So it's good. Yes, here we have a biparty graph. Okay, so v1 is connecting to v2, v4, and v3 is connecting to v2, v4 as well. So we have biparty graph. So we notice that in a biparty graph, the vertices in the same set, they don't have an edge. They're not adjacent to each other. Okay. But if we have a triangle, let's see what happens. So let's say v1 is in x1, and then, well, because v2 is connecting to v2 is adjacent to v1, so v2 should be in x2. But v3 is also adjacent to v1, it should be in x2 here. Well, but there's a contradiction because now you have v2 and v3 are adjacent. This is a contradiction. So far, so good. For all the vertices in the same set, they're not adjacent to each other. Okay, there's no edge between them. Why is that? Let's go back to the definition of biparty. So the graph is biparty if there exists subsets x1 and x2, and x1 and x2 they are distinct. Distinct means they don't share common vertices. Okay, they have different vertices, and their union is V. Then each edge is incident to one vertex in x1 and one vertex in x2. So all the edge must incident to one vertex in x1 and one vertex in x2, and those are all the edges. So you cannot have a edge is incident to two vertices in the same set. Okay? So that means we allowed rectangles, but we don't allow triangles. But what happened here? We have a triangles. So triangle is not allowed. Okay? And if you want to write down a formal proof, so this is the formal proof we want to show by contradiction. Okay, so we're gonna look at that triangle. So V4, V5, V6. Okay, so because V4, V5 are adjacent, let's say V4 is in x1. Okay, then we have V5 in x2. Okay, so now because V5 and V6 are adjacent, then and V5 is in x2, then V6 must be in x1. Okay, and also because V4 and V6 are adjacent, then because V4 is in x1, V6 must be in x2. Whoa, contradiction. Now, see, we have shown V6 is in x1 and x2. And this is a contradiction because x1 into x2 should be empty sets. Okay, they should be disjoint. So that's why we get a contradiction. Okay, and therefore, so the graph is not biparty. So far, so good, everybody. Okay, and then next, draw the complete biparty graph K24. Well, what is K24? It means x1, we have two vertices, x2, we have 4 vertices. Let me draw a bigger one. Okay, then completes, right? So each vertex here is connecting to all the vertices in x2. You can see the edges cross, and there's no way to avoid this happen because there are a lot of edges. Okay, and it's okay, just leave it like that. So this is the complete bi-party graph K24. And this is sessions 8.1. So try to do your homework, and if you have questions, feel free to take pictures and ask me in class or office hours or email me. Have a nice day. Bye.